The future belongs to those who understand data, and every click, every number, every decision, and powered by intelligence. With Python, you don't just analyze data, you control it. You visualize it, and you turn it into opportunity. At EDXcellence, we train you with real-world projects and practical skills. Master data science with Python. Build your future with EDXcellence.
Junior-level data science is often mistaken for the isolated act of running algorithms. Structurally, the field functions as a rigid, iterative operational pipeline. The objective is the translation of an abstract business constraint, like unexplained revenue loss, into a deployed, predictive mathematical model. This requires moving from chaotic raw data ingestion at one end to a clean, real-time analytics dashboard at the other. To build a predictive system that survives in a live environment without degrading, every stage of this architecture must be mastered. This architecture is comprised of 6 interconnected nodes, spanning from initial problem understanding to continuous monitoring. Rushing or skipping any single stage breaks the chain, ensuring a system failure once the model reaches production. Step 1 is business problem understanding. No data is touched until core objectives are locked. You must identify strict constraints, execution time, budget, and data availability. For example, revenue loss must be translated into a data science task with a strict accuracy metric. Once the parameters are set, the pipeline moves to step 2, data acquisition. This is where raw information enters the system. Modern data scientists rarely rely on manual entry, sourcing datasets instead from external integrations or repositories like Kaggle. The primary tool for modern data ingestion is the Application Programming Interface, or API. When a user logs into Blinkit, an API pulls stored address parameters directly from Zomato. This bypasses redundant local database management. Data is pulled on demand. Establishing a rigorous problem metric and automated ingestion flow forms the structural foundation required before any analysis occurs. With the raw materials acquired, the pipeline moves to step 3, data processing and cleaning. Raw ingested data is inherently messy and unstructured, making it hostile to algorithmic logic. The first cleaning protocol is imputation. Empty cells in the data grid are systematically filled using an automated filter. These null gaps are resolved using the mean, median, or mode. Next is deduplication. Repeating records are stripped out to prevent severe statistical bias. And the third protocol is normalization mapping. Normalization forces wildly disparate numerical features into a single, standardized scaling range. This allows the algorithm to process various data types evenly. This phase is also where extreme outliers are neutralized. The rigor applied during this cleaning phase acts as the primary gatekeeper for a machine learning model's ultimate predictive efficacy. The pipeline moves forward to step 4, exploratory data analysis, or EDA. The objective is to identify the underlying relationships and distribution of variables before any modeling begins. Data visualization is the essential tool used to observe these patterns. Scientists utilize histograms for distribution, scatter plots for relationships, and heat maps for a dense correlation matrix. These visualizations expose critical correlations, like proving specific discounts directly correlate with sales spikes. These discoveries dictate which features will drive the final algorithm. EDA acts as the critical bridge that transitions these perfectly cleaned rows of data into a highly strategic architectural blueprint for the machine. Step 5 is modeling and prediction, the mathematical engine of the pipeline. Modeling begins by selecting the specific data features identified during the EDA phase. The process splits data unequally. A massive segment routes into a training node, while a smaller portion is quarantined in a testing node. The algorithm absorbs the training data to learn specific patterns. Then its predictive accuracy is evaluated strictly against the unseen test data. The nature of the business problem determines the architectural type of model deployed. Use regression for continuous values, classification for categorizing distinct groups, and clustering for discovering underlying similarities. While modeling represents the heavy mathematical lifting, its success relies entirely on continuous validation against real-world inputs. This leads to the final pipeline node, Step 6, deployment and monitoring. The trained model is pushed into production environments via real-time dashboards and API integration. In the banking industry, a live API continuously scans a massive stream of incoming credit card transactions in real time. The system classifies transactions as genuine or fraudulent based on the historical rules it absorbed during training. However, consumer behaviors and fraud patterns constantly evolve. This divergence is known as data drift. It occurs when the live data no longer matches the model's original training baseline. Because of this drift, continuous monitoring is mandatory to detect spikes in false alerts and declining accuracy metrics. Detecting data drift triggers a retraining loop, pushing updated, modern data back into the modeling phase. The data science lifecycle functions as a self-correcting feedback loop, maintaining